My chosen engineer is Mona Salim, who was the first female structural engineer to work in the UAE. She began her career in 1980 and is now the technical manager of the engineering division at BSBG. She pursued engineering due to her love of maths, problem solving, and a passion to bring things to life. She is nicknamed by colleagues as a human computer. Her experience and roles suggest that she is technically competent and will oversee all structural solutions. Mona Salim's firm was lead consultant for the design of a luxurious private school on Al Reem Island, Abu Dhabi. It accommodates 1,800 pupils and is situated on a 25,000 square meter plot. The client wanted specialist facilities with large volumes of space. This resulted with two main buildings, one for teaching and another for sports. The teaching block is a 4-story building with a large central atrium and a basement car park. The sports block is a single-story structure, approximately 10 meters in height with large uninterrupted spans. The key drivers of the project drove many of the structural solutions of the building. The client strives to be a global leader in private education, so wow factor was important in design. This is mainly expressed by long spans, a 4-story atrium, cantilever stairs, and extensive sport facilities. In the teaching block, the atrium tapers in width from 7.5 to 15.5 meters. These roof spans were achieved using a transfer truss system. The surrounding floors are supported on a steel frame where spans vary from 8 to 10 meters. The sports block required long spans of 45 to house numerous facilities similar to the Bath STV. This is achieved using Warren truss beams. The roof needed to be flat as the site could not house all required facilities. Surrounding roads drove design vertically. Another key driver was rapid construction, as the client needed the project to be constructed within a year to be ready for the new school term in 2017. This is why there are many repeating elements, prevalent on the atrium roof truss, where members were the same regardless of span. Legislation in the UAE requires all new build projects from 2010 to achieve at least 1 Pearl rating. Examination of these requirements show that the achieved mandatory credits focus on reducing operational carbon rather than embodied. This may have influenced design. Overall, few innovations could be identified due to drivers. As a result of drivers and solutions, embodied carbon of the building was significant. In total, it was almost 15,000 tons of CO2. In the teaching block, steel elements were responsible for the majority of embodied carbon. For the sports superstructure, it was a composite roof. From these findings, carbon reduction could be achieved by making changes in structural design. In the teaching block, spans were reduced to 6 meters, different materials were selected, and the atrium roof was changed to a grid shell structure. The change in span made drastic reductions of carbon. 6 meters still give a sense of large space while being more economical in terms of carbon. Reducing spans meant beam sections and columns became lighter as they resisted lower loads overall. Also, all new members were sized with UFs closer to 1 rather than 0.8, which is standard in industry. A regular grid was assumed throughout the building, so quick construction is achievable. Use of virgin steel was assumed in the improved carbon calculations, as sources of locally recycled steel is scarce. Regardless, carbon savings of over 3,500 tons were achieved for the primary steel frame. Changes in materials, particularly the concrete and cladding, also decreased overall embodied carbon. Lightweight ceramic cladding replaced GRC panels to achieve similar aesthetics and made savings of 240 tons. Concrete with 50% GGBS replaced general mixes. Only GGBS seems to be commercially available in the UAE, so potential further savings using other blends are not always feasible. The atrium roof was also converted to a steel grid shell, which halved the element's carbon as the truss system was structurally inefficient. Timber grid shells were initially considered, but due to a lack of local supplies, this was deemed inappropriate. In the sports block, several options to reduce carbon were explored. Initially, a steel grid shell roof was considered, but because of large spans and forces, member size increased, meaning carbon savings were insignificant. Also, a curved grid shell reduces the roof area required by sport facilities. Instead, the composite roof was changed to precast planks to reduce carbon, maintain required facilities, and ensure ease of construction. Further, reducing the entire building height by 1 story could reduce carbon significantly. Access between the teaching block and pool viewing area was probably why the pool was triple-story, which felt quite large. This change reduced carbon by over 70 tons. Overall, the changes to both buildings resulted in savings of over 5.5 tons of CO2. Other measures to improve the building's whole life carbon should be done to achieve a higher Pell rating. This would further the building's status and align with the client's goals. I believe the building is an example of how key drivers can conflict with low-carbon design and hinder structural innovation. Unfortunately, this building type may be common in practice, but minor structural design decisions can alter the project's trajectory towards sustainability.